So this is the schematic. Don't look at the values at the moment. This is the schematic we used for model-based biasing. Yes, we had one transistor that and a loop around it that determined the bias, and then we have another transistor that is doing the amplification. And here we have to drive the load, and I simply assumed here that the load is 50 ohm. Of course, now the load, in this case, from a bare CS stage, will not be driven from 50 ohm, and that was also the question. But there are other means to do that. I could make, for example, two feedback loops and setting the output impedance exactly to 50 ohm if I make a negative feedback amplifier. Then I would need to set A and C and have a nice 50, B and D and have a nice 50 ohm output. But I could also decide to make a voltage type output of my amplifier and then make RL 100 ohm consisting of 50 ohm extra to create 50 ohm output impedance of my voltage amplifier that originally had only 0 ohm. So I just do brute force impedance matching at the output, and in series, of course, the cable. So then it would be 100 ohm. Another case is to say, no, I make an amplifier with a current output, and then I put 50 ohm in parallel, creating 50 ohm output impedance, and then driving the load. And then effectively, I have to drive 25 ohm. So this can all be checked with the same circuit, because it's just, the whole thing is parameterized. And here you see, I have chosen for, oh, I see RL is 10K. That's a little bit wrong. I should choose RL is 50 ohm, and RS isn't there anymore because the current source is removed. So this one can be deleted. Oh, that doesn't work that way. Okay. RS 50 and RL is, so now it should go. Okay, so what I'm interested in is the following. Probably this stage, the output stage, or the stage that will drive the load, needs to be driven either from the antenna or from another input stage. The antenna doesn't produce that much voltage, but I can also put another stage in front of it, and then it can have more input drive. But I can never get more input drive than 1.8 volt peak to peak, because the stage in front of this stage also has to be supplied with 1.8 volt power supply. So the first thing that I need to do is to be sure that I can design a transistor that can operate within 1.8 volt for the given current. Now, if you calculated yourself the current required, we need for 0 dBm output at 50 ohm, which is 225 millivolts RMS, about 320 millivolts peak to signal. 320 millivolts peak signal over 50 ohm means 6.4 milliamps. So I could start, and of course that is not very handy, because if you do 6.4 milliamp, then you have no reserve anyway. So usually you take some reserve, and this is not science, this is just an engineering matter. We are going to optimize it later anyway, and I put here 8 milliamps. Now I did, cancel. I did a width, a length, the shortest length possible, that gives me the lowest drive voltage. And at this moment, I have no other requirements. I'm not interested in bandwidth, not interested in distortion, only in clipping, in drive capability. That's another issue. So I want 320 millivolts across 50 ohm, and which corresponds with 6.4 milliamps. So, and I put the output here to make it, let's say, the largest possible swing at 0.9 volt operating. You need at least 320 millivolt, but since there's 1.8 volt available, I just put it halfway the power supply. Well, let's start with some width. I did 10 micro, and 10 micro just to show you what happens. So if you do with 10 micro and you simulate here, and I don't even want to see the transient because I see already in the circuit that for that it wants to create 5.7 volt at the gate, and that's not available. So the width of 10 micro is too small. It cannot be biased such that the output current is 8 milliamp. I need more. Well, we can do the factor 2, yes. In this case, I do the factor 5. Okay, but this is just also optimization stuff, which is not so difficult because it converges quite easily. And now, if we before looking at the transient view here at this stage, it's 1 volt. So the peak voltage that I can apply cannot be more than 0.8 volt to drive this stage, because then I'm within 1.8 volt and that is all I have. So let's drive it with 0.7 volt or 0.75. That will really be the limit, and see if it now can drive the load. So we run it again, and then I press this probe here and see it has 360 millivolts on top and 550 millivolts there. So it clips at a value higher than 360 milliamp, so it works. And now what you can do is optimize. Of course, it clips here, but that is not really of interest. There will be a lot of distortion, but anyway, if you make it smaller, if you make the width smaller, this range will drop. And if you make it wider, then you need less drive and it becomes more linear. That is basically what you had to do for this exercise. Now, maybe a question to you, or a question or a remark, something you should be aware of. If this current, the operating current now is 8 milliamps, so if the voltage has its maximum negative value, then the current through the transistor is much more. It is like the voltage that is left here, this voltage, and the negative voltage, of course, this one divided by 50 ohm. So the current in the transistor, oh, that's not how it works. Yeah, it is how it works. You see the current is here, it switches completely off. Yeah, and it goes to 18 milliamps. So it takes 10 milliamps plus the 8 milliamp of the operating point. So now the rest is tuning, but we have basically a CS stage, we have the width, we have the operating current, and we can drive the load of 50 ohm. If you want to drive 25 ohm, you find another value. If you want to drive 100 ohm, you also find another value. But this is basically the idea of this exercise.